Right, so we are going to start the discussion of 2005 essay question. Right, figure shows a satellite having a cylindrical body S and two identical solar panels. Right, the two solar panels are identical, similar to each other. Right. This satellite is moving in the space where gravity is negligible. Okay, and rotates about axis of xy with the cylinder with an angular velocity of 6 revolutions per minute. So angular velocity is given in RPM. You see, the satellite has a body, a cylindrical body, and two solar panels. The plane of the solar panel is perpendicular to the xy of the satellite of the cylinder. The radius of the cylinder r equals 0.4 meter, and moment of inertia of the cylinder about xy axis is 6 kgm square. So it means cylindrical part, the moment of inertia of the cylindrical part is given as 6 kgm square. For each solar panel, mass 2 kilogram, length A. What is A? This one. This length A is 1.2 meter, and width that should be simple B. That's a typing mistake. Not simple D, but simple B. Right? For each solar panel of mass 2 kilogram, length 1.2, width simple B 0.6 meter. The moment of inertia of each solar panel, the moment of inertia of, let me keep the question like this. The moment of inertia of each solar panel about xy is given by m a square plus b square divided by 12 plus m into r times a over 2 and square of everything. So that's what they have given. I think the board is clearly seen. The given equation, the moment of inertia of a panel is given by the equation a square plus b square divided by 12. So this is 2005 AL first question, which is given from mechanics lesson, right? The moment of inertia, right? Equation is given by Roman number 1, the moment of inertia of a panel, of a solar panel, that is given by the equation simple m into a square plus b square divided by 12 plus simple m into capital R plus a over 2 square. Please check whether this equation is correct. Please check whether the equation is correct. So that's what they have given. You must have the tune or you must have the image of the question. Check the WhatsApp group. Right. Simple M is given as 2 kilogram. Simple M is given as 2 kilogram. A is given as 1.2 square. A is 1.2. B is 0.6. B is 0.6. We should get square and we should divide it by 12. So this is a given expression. This does not give us the entire moment of inertia of the satellite. It gives only the moment of inertia of one solar panel. Right. So plus simple in 2 kilogram, that is the mass of a panel, R, radius. Radius of the cylindrical section, that is capital R, which is given as 0.4. Plus A is 1.2, we should divide it by 2 and we should get square. Now you see, this 2 and 12 can be cancelled out. That's the first thing that we are able to do. 12 divided by 2 is 6. Square of 1.2 is 1.44. That is square of 12, we know that 144. There should be 2 decimal places when we consider 1.2. Square of 6, 36. But square of 0.6, there should be 2 decimal places, 0.36. Plus 2 will be there. This is 0.4. Plus 1 divided by 2, 0. 12 divided by 2, 6. And square of this. So we will obtain 4 plus 6 is 10. 1 remaining. 3 plus 4 is 7 plus 1 is 8. Am I right? 6 plus 4 is 10. 1 remaining. I have written 0, 1 remaining. 3 plus 1 is 4. 4 plus 4, 8. No remaining. This is 1 and we should divide this by 6. This is 2 into 0.4 plus 0.6 means 1.0. If you add them. Right? This is square. Right? So then you will obtain 1.8 divided by 6. 1 divided by 8 is 1 divided by 6 is 0. 18 divided by 6 is 3. Plus square of 1 is 1. 1 into 2 is 2. So 2 plus 0.3 means 2.3. Unit is kgm square. So moment of inertia of a panel is 2.3 kgm square. Is right in here? Some students may not be in the class last week. There are some new students, that's why I did this calculation. Right? Is completed there? Right. So we have found only the moment of inertia of one panel. But what's the total moment of inertia of the entire satellite? That's what they have asked. The moment of inertia of the complete satellite. Moment of inertia of the complete satellite means the summation of the first panel, IP1, moment of inertia of the first panel, plus moment of inertia of the cylindrical body, plus moment of inertia of the second panel, IP2. IP1 means moment of inertia of the first panel, IP2 moment of inertia of the second panel. Moment of inertia of both panels same, identical panels. Therefore, moment of inertia of the first panel 2.3, moment of inertia of the body is 6, moment of inertia of the second panel is 2.3. So 6 plus 2.3, 2.3 means 4.6. 4.6. 4 plus 6, 10. So that is 10.6 kgm square. So this is the moment of inertia of the entire satellite. Complete India. This is the moment of inertia of the entire satellite. Right? Right. What about the second question here? This is the answer for Roman number 1. That is, they asked us to find the moment of inertia of the satellite, the entire satellite. We did it. The second question, let me check the second question here. Roman number 2, calculate the rotational kinetic energy of the satellite. I think you are able to see the question. Calculate the rotational kinetic energy of the satellite. Here they have given the angular velocity in RPM. As I remember, it is given as 6 RPM. Let me check. Yeah, you see, the angular velocity is given as 6 revolutions per minute, RPM. So if RPM value is given, if they ask us to find the angular kinetic energy, first of all, we should convert this RPM into radian per second. Let us do it first here. Right, can somebody tell me the equation that we use to convert RPM into radian per second? What is the equation? I want to convert this RPM into radian per second. Somebody unmute the mic and give me the equation here.
RPM into 2 pi over 60.
RPM value multiplied by
2 pi over 60.
2 pi over 60. Very good. So, angular velocity of the satellite, the RPM value should be multiplied by 2 pi over 60. Then the unit converted into radian per second. Right. I want more space to write. Therefore, I will erase this sentence. I'm going to erase this. If you want any more time to write the things that I have written in blue color, you may take a screenshot. I'm going to erase it. Right. Look at board. The RPM velocity is given as 6 revolutions per minute. 6 into 2 pi by 60 radian per second. Now you see the change. 6 and 60 can be cancelled out. 2, 5 means 3.14 divided by 60 divided by 6 is 10. Can you understand that, Maxine? 60 divided by 6 is 10. 2 is 2, 5 is 3.14. If I multiply 3.14 by 2, I will get 2 times 4 is 8. 2 times 1 is 2. 2 times 3 is 6. 6.28 divided by 10. If you divide this by 10, another decimal place is added. So finally, angular velocity will be 0.628 radian per second. Complete this here. This is the first thing that you want to do, because to calculate angular kinetic energy, the velocity should be in radian per second. Start. Right, now let's calculate the angular kinetic energy. Now it's so easy to calculate the angular kinetic energy of the satellite. Look at board. Angular kinetic energy of the satellite. But in the exam, do not write KE, please write angular kinetic energy of the satellite. Equals half I omega square. This is the definition. I think you remember this equation when we start teaching moment of inertia. We have used this. Angular kinetic energy is half I omega square. So this is half moment of inertia of the satellite. We found it. You see, moment of inertia of the satellite was found as 10.6. 10.6. Into omega, we have found omega as 0.628 omega square. So we should get the square of this. I'll give you a very big help. 10.6 divided by 2. 10 divided by 2 is 5. 6 divided by 2 is 3. Should get the square of this value and you should multiply it by 5.3. Try it and send your answer to my Zoom chat. Simplify this, send your answer to my Zoom chat. I'm waiting for you. Right. Let me give you a small help. 0.628 square is 0.394384. 0.628 square is 0.394384. But it is not necessary to keep this much of decimal places. The maximum number of decimal places needed for this question is 3. You must stop with 3. Therefore, this should be written as 5.3 into 0.394. But you should not take 2 decimal places. There should be 3 decimal places for such a moment of inertia question. So keep up to 3 decimal places, multiply and send me the answer. No need to use 6 decimal places. That is useless. Do not forget to keep the unit joule. If you simplify this, you get the answer. You should write answer only up to 3 decimal places. Do not forget it. So that is 0 or 2.088. No need to keep more than 3 decimal places, but do not keep less than 3 decimal places. Please keep the answer up to 3 decimal places. Complete this here. In the examination, if you have kept the answer as 2.09, that's okay. 2.09 is also okay. Right. Now let's go to the next part of the question. Let me show you the next part of the question. Right. So you will get these questions in third test here. Normally, past paper questions are slightly edited and given them as the term test questions. Right. So you should fully understood this question. Let me show you the next question here. Right, I think you are able to see this. So we have answered Roman number 1, Roman number 2, now Roman number 3. If the two solar panels are folded so that the new moment of inertia of each panel about xy becomes 1/4 of the previous one. So solar panels are folded. Then what has happened? The moment of inertia of each panel becomes 1/4 times the previous panel. Calculate the new moment of inertia and the new angular velocity of the satellite about xy axis. Right. Let me use the normal whiteboard. I want to erase some of few of the things. If you want any more time to write these things, please take a screenshot. I'm going to erase this black color section. Right. Look at board. Right. We are discussing 2005 first essay question, which was given from mechanics lesson. In Roman number 3, they have said that, listen here, this is the cylindrical body of the satellite. And there are two panels. Let me draw it like this. This is enough. And this satellite is rotating. The satellite is rotating about this axis with an angular velocity of 0.628 radian per second. So this is the omega. We have found it. The moment of inertia of this satellite at this time, let's say I1, the moment of inertia of this satellite, we have found it as 10.6. 10.6 kgm square. While it is rotating like this, right? While it is rotating like this, it does something like this. The two solar panels, let's say my hands are two solar panels, they are folded. Then the moment of inertia reduces, right? So once the solar panels are folded, they will be shorter, like this. Right. Now we want to find the new moment of inertia of the satellite, I2. This is the first thing we want to find. The next thing that we want to find is the new angular velocity. So let me mark the new angular velocity as omega dash, radian per second. So in the exam, not necessary to draw a figure. It's not necessary to draw a figure. But once you draw a figure, it's very easy for you to understand the story. As it is very easy for you to understand the story, draw it there. Draw the figure for Roman number 3. Right now, how do you find the new moment of inertia of the satellite? To find the new moment of inertia of the satellite, we should find the new moment of inertia. The new moment of inertia of a panel. This is the first thing you want to find. And the other thing, only the panels are folded. Only the panels are folded. The cylindrical body cannot be changed. So it means the moment of inertia of the cylindrical body remains unchanged. Only the moment of inertia of panels are changed. So it is saying that the new moment of inertia of a panel is 1/4 of the previous value. The moment of inertia of the previous one is 2.3. So this is the moment of inertia of a panel. Then what about the new moment? The new moment of inertia of the two panels. There are two panels. The new moment of inertia of the two panels. How do we find? Somebody please tell me again. I want to find the new moment of inertia of the two panels. How do we find it here?
Multiply by 2.
Yes. Speak loudly.
Multiply by 2.
Multiply by 2. Yes. Moment of inertia of one panel is 1/4 into 2.3. Therefore, moment of inertia of two panels mean it should be multiplied by 2. Moment of inertia of one panel 1/4 times 2.3. Moment of inertia of two panels means should be multiplied by 2. Now you should understand that this 4 and 2 can be cancelled out. 1/4 divided by 2 is 2 into 2.3 into 2.3. Then let's divide. 2 divided by 2 is 1. 3 divided by 2 is also 1, but 1 remaining. Then we have put the decimal places. That one becomes 10. 10 divided by 2 is 5. So 1.15 kgm square is the moment of inertia, the new moment of inertia of the two panels. Write the two statements quick. Just write the two statements. Right. According to this, now what should be the new moment of inertia of the satellite? Earlier moment of inertia was 10.6. Now the panels are folded. Therefore, what should be the new moment of inertia of the satellite? the new moment of inertia. The new moment of inertia of the entire satellite. The new moment of inertia of the satellite is moment of inertia of the body. Moment of inertia of the body did not change. Plus moment of inertia of the panels. I use the plural word. Panels, 2 panels. So moment of inertia of the body remains unchanged as 6. Moment of inertia of the panels. Moment of inertia of the panels 1.15. So 6 plus 1.15 means 7.15. Do not forget to write the units in kgs. So this is the new moment of inertia of the panels. Completed here. Right. Now we know the initial moment of inertia. We know the final moment of inertia. We know the initial angular velocity. We want to find the new angular velocity. What should I do here? What should I apply to find the new angular velocity? What's the law that should I apply? Somebody?
Law of conservation of angular momentum.
Very good. Excellent. So what is the thing that we should apply? Let me write. Let us apply. Please write with me. Please write with me. Do not wait. Let us apply the law. The law of conservation. The law of conservation of angular momentum. Angular momentum. So what does the law tell us? What does the law tell us here? Initial total angular momentum equals the law of conservation of angular momentum. It tells us initial total angular momentum equals the final total angular momentum. Angular momentum is the product moment of inertia into angular velocity. Linear momentum is the product mass into linear velocity. Here, linear momentum equals to mass into linear velocity. Angular momentum, moment of inertia into angular velocity. Right. So this law tells us initial total angular momentum. Initial total angular momentum. Initial total angular momentum equals final total angular momentum. Got it? Initial total angular momentum means moment of inertia I1 into angular velocity omega. Final angular momentum, moment of inertia I2 into the angular velocity omega dash. Apply this equation, write down everything, apply this equation, find the value of omega dash, send your answer to my Zoom chat. Start there. I want to check whether you know it. Do it yourself. Right, I1 is 10.6, omega 1 0.628, I2 7.15 into omega dash. Just take 7.15 to this side, then you can find omega dash. So as I do not have enough space, I'll write the next step here. So therefore omega dash equals right, take 7.15 this side, so that is 10.6 into 0.628 divided by 7.15. I can give you help. I'll give you help. So let me divide 10.6 by 7.15. If I divide 10.6 by 7.15, the answer is 1.482. If I divide 10.6 by 7.15, the value is 1.482. 1.482. Now the remaining number 0.628. So once we multiply these two, we will obtain the angular velocity, the new angular velocity in radian per second. Try it. Try to multiply them. Let's round off the final answer up to 3 decimal points. Then you get 0.93. Here you have 0 and 1. So you should round off. Then you get 0.931. It's better to round off the final answer. It's better to round off the final answer. Keep it as 0.931. Even you write 0.930, it's okay. But let's keep it as 0.931. Rounding off. Because here 0.628, here 0.931, like that. Who got this answer? Please raise your hand up if you have obtained this answer. Lamai, please raise your hand up if you have obtained this in the Zoom chat. Very good. I'm so happy. Nice. Excellent. Complete the note. Right, now we know the new angular velocity. Now we know the new moment of inertia. So now we can calculate the angular kinetic energy of the satellite. Right. If anybody wants any more time to write these things, I'm going to erase. If anybody wants any more time to write these things, please take a screenshot. I'm going to erase. Right. So let's find the new angular kinetic energy of the satellite. The new angular kinetic energy. In the exam, please do not write KE, write kinetic energy, right? The new angular kinetic energy is half into I2, the moment of inertia I2 into new angular velocity is omega dash square. Half into I2 into omega dash square. So half the new moment of inertia 7.15. The new moment of inertia is 7.15. Omega dash, we have found omega dash as 0.931. 0.931, but we should get the square. Right? So some calculations are there, yes. I'll give you help. I'll definitely give you help. Look at what it. 7 divided by 2 is 3. 1 remaining. With that one, this will be 11. 11 divided by 2 is 5. Again, 1 remaining. With that one, this will be 15. 15 divided by 2 is 7. Again, 1 remaining. 10 divided by 2 is 5. So you just get the square of 0.931. Put here with only 3 decimal places. Get the square of 0.931. Use only 3 decimal values. Use only 3 decimal places. Multiply and give me the answer. So I have helped you. Send your answer to my Zoom chat. Send your final answer to my Zoom chat. Try it. If you get the square of 0.931 and if you round off it up to 3 decimal places, it should be 0.867. It should be 0.867 if you round off it up to 3 decimal places. Now you just want to multiply 3.575 by 0.867. It should be multiplied by 0.867. That's what you want to do. Right? Then if you multiply that 0.867 into 3.575, 0.8867 into 3.575 to get the answer as 3.099. Am I right here? Yeah, 3.099. The new angular finding is 3.099 joules. Shall we check the calculations again? Let's check from the very beginning whether we have made any mistake. I think that there are no mistakes, but it's better to check. It's correct. Yeah, it is correct. Now let's go to the next part of the question. Let me show you the next part of the question there. The next part, Roman number 4, Roman number 3, we have answered. Right. Roman number 3 we have answered. Now we should try for Roman number 4. In order to control the rotation of the satellite, a mechanism is available to apply a torque on the satellite along XY. This mechanism does not change the moment of inertia of the satellite. There is a mechanism. It does not change the moment of inertia of the satellite. It only applies a brake, the torque. Actually, there is no Roman number 5. Actually, this is the Roman number 4. This is the rest of the question. And this is Roman number 5 like that. Right. Now you see, in order to control the rotation of the satellite, a mechanism is available to apply a torque, curl T or torque, Greek letter, on the satellite along XY. This mechanism does not change the moment of inertia of the satellite. Okay. If the angular velocity of the satellite has to be brought back to its original value. So earlier its angular velocity was 0.628. The new angular velocity is 0.931. So it means angular velocity has been increased. So we apply a torque. Actually, it should be a braking torque because it reduces the angular velocity. As the angular velocity is reduced from 0.9 to 0.6 something, it means it's a braking torque. If the angular velocity of the satellite has to be brought back to its original value, from the value calculated in Roman number 3 above, by maintaining a uniform angular deceleration for a period of 5 minutes, calculate the magnitude of the angular deceleration and the torque required. Within 5 minutes, we apply a braking torque. Within 5 minutes, we reduce the velocity from 0.931 to 0.628. They ask the magnitude of the angular deceleration. Velocity reduces mean angular deceleration and the torque required. Right? Let's give word right here. Let's give word right. Right. Now, the new thing, Roman number 4. Roman number 4. The satellite is there. Its solar panels are now folded. The solar panels of the solar panels are folded. The new angular velocity, omega. You can use any letter, omega 1, omega 2, anything. Right? So, omega 1 is 0.931 radian per second. Right? This is the new angular velocity. Now we are talking from this situation. So it is omega 1. It's okay to use omega 1. And we apply a braking torque. We apply a torque for a period of 5 minutes. For a period of 5 minutes. Then angular velocity reduces. Then angular velocity reduces from 0.931 to, let me mark this as omega 2, 0.628. 628 is the previous value, original value at the beginning. The original angular velocity of the satellite at the beginning is 0.628. But the new angular velocity is 0.931. So we apply a braking torque, we reduces the velocity from 0.931 to 0.628. To do it, it takes 5 minutes. So we want to find the torque and we want to find the angular deceleration. Right? So easiest way to find angular deceleration is omega 2 equals omega 1 plus alpha t. Here, alpha is acceleration. In this equation, alpha is angular acceleration. So once you find angular acceleration value of alpha, if it is a deceleration, alpha should have a minus. Alpha is angular acceleration. So you apply this equation and try to find the value of alpha. If you get a minus value for alpha, it's a deceleration. Draw this figure, try to find alpha, and send your answer of alpha to my Zoom chat. Then I can check whether you have understood or not. Start there. Is it very difficult? And only very few students send me the answer. Why is that? Is it that much difficult? I can't believe it. That should be very simple, right? It should be very, very simple. Let me check. Omega 2 is 0.628. Omega 2 is 0.628. 0.628. Omega 1 at the beginning, before we apply the torque, velocity is 0.931. After we have applied the torque for a period of 5 minutes, the angular velocity is 0.628. Right, so final velocity is 0.628, initial velocity is 0.931. We don't know what the alpha is. But when you apply time, you should be very careful. 5 minutes, this should be converted into seconds. Therefore, 5 minutes should be multiplied by 60 to convert minutes into seconds. Now I will do something like this. I don't do anything to this 0.628. I don't do anything to 0.931. 5 times 60 is 300 alpha. I'll take this 300 alpha to this side. I'll take this 300 alpha to this side. So it will become minus 300 alpha. 0.931. 0.931. I'll take this 0.628 to this side. 300 alpha to the other side. 0.628 to this side. Positive 0.628 come to this side as minus 0.628. So 300 times alpha equal, let me subtract. This is 1. 1 minus 8 cannot. You have to take 1. So 11 minus 8 is 3. This is 2. 2 minus 0. 2 minus 2 is 0. This is 9. 9 minus 6 is 3. 0. Like this. Now take 300. Minus 300 the other side by cross multiplication. Then you can find alpha. So you get alpha equals 0.303 divided by minus 300. Not easy to divide, right? So I'll keep the minus sign here. I divide 300 by 100. If you divide 300 by 100, answer is 3. I have divided denominator by 100. So I should divide the numerator should also by 100. So if you divide 0.303 by 100, the answer will be, there should be 2 decimal points will be added, give the 2 zeros of 100, and this is 0.303 will be there. So finally you get minus 0 divided by 3 is 0. This 0 divided by 3 is 0. This 0 divided by 3 is 0. 3 divided by 3 is 1. Answer is enough up to 3 decimal places. Do not divide any further. Just stop with the third decimal place. So answer is radian per square seconds. Who got this answer? Please raise your hand up if you have obtained this answer. Lamai? Please raise your hand up in the Zoom chat if you have obtained this answer. Right, what is the meaning of the minus sign here? So alpha is actually the acceleration. So what is the meaning of the minus sign? Can somebody unmute the mic and tell me? For the alpha, we have obtained the answer with the minus sign. What does it mean? Lamai? What is the meaning of the minus sign of alpha? Can you hear me? What's the meaning of the minus sign of alpha? Somebody please unmute the mic and tell me. Okay. Let me change. Somebody unmute the mic and tell me the meaning of the minus sign. I didn't hear you.
Deceleration.
Yeah, it is deceleration. That is deceleration. So put a star point and write. Alpha is the angular acceleration. Alpha is the angular acceleration. Alpha is the angular acceleration. Full stop. Alpha is the angular acceleration. The minus sign of alpha. Alpha is the angular acceleration. The minus sign of alpha. The minus sign of alpha indicates that alpha is the angular acceleration. Full stop. The minus sign of alpha indicates that the object has an angular deceleration. Alpha is the angular acceleration. Full stop. The minus sign of alpha indicates that the object has an angular deceleration. The object has an angular deceleration. Next star point. Next star point. But in the torque equation, the minus sign of alpha is not used. But in the torque equation, the minus sign of the alpha is not used. But in the torque equation, the minus sign of alpha is not used. Right. So we just write torque equals IR. The minus sign means velocity decreases. So if you want, you can say braking torque. The positive negative signs of the alpha only used in angular equations, such as omega 2 equals omega 1 plus alpha t, theta equals omega 1 t plus half alpha t square, omega 2 square equals omega 1 square plus 2 alpha theta. In those equations, we use positive negative signs of alpha, but in the torque equation, we do not use the minus sign because it is meaningless. Right. The moment of inertia of the satellite, the new moment of inertia of the satellite is 7.15. Alpha is found as 0.001. 0.001 can be written as 7.15. 0.001 means how many decimal places do you have? 1, 2, 3. So 0.001 can be written as 10 to the power minus 3. The unit of torque is Newton meter. So this is the required torque to reduce the velocity from 0.931 to 0.628 within 5 minutes. Complete this here. Complete it. Right. Now let's go to the final question there. We have reached to the end of the question. Let me show you the final part of the question. The final section of the question, right? Actually, this is the Roman number 5. This is not Roman number 5. So Roman number 5 asks, determine the energy required to bring the angular velocity of the satellite back to its original value. What they have asked us to find here, how much energy is required? That's what they have asked. How much energy is required to bring the angular velocity of the satellite back to the original value? Back to the original value means 0.628. They asked us to find the amount of energy needed for this process. Okay, let's give a try. Right. The amount of energy needed for this process is equal to the amount of work done by the torque. Energy needed for this process to reduce the velocity from 0.931 to 0.628, it is equal to the amount of work done by the torque. Work done by the torque is equal to torque into angular displacement. So first of all, we should find angular displacement. To find the angular displacement, we can use the equation theta equals omega 1t plus half alpha t square. Omega 1 means this velocity, starting velocity. Starting velocity of during this process, during the period of 5 minutes, at the beginning of the 5 minutes time period, the angular velocity was 0.931. So omega 1 is 0.931. The time taken for this process, 5 minutes. So this should be multiplied by 60 to convert minutes into seconds. Plus half alpha. Now we should use the minus sign of alpha. Positive, negative signs of alpha used in all the velocity displacement equations, right? So alpha is minus 0.001. This is alpha. Time taken is 5 minutes. Therefore, it should be multiplied by 60. This is the seconds. T square. Therefore, we should obtain the square. So use this equation and find the angular displacement. Do it yourself here. Find angular displacement and send me your answer to the Zoom chat. Start there. Okay, many of you have sent me the answer. I'm very happy. Good, right? So you're working very well, right? You're working so well. Good. Keep it up. Right. Look at board. So that's why when normally students obtain the answer without my help, normally I give the time for them to work. I give the time to work alone if it is appeared that you are working. So good, happy. So 0.931, look at both. 0.931 can be written as, I just want to show you the simplification process here. Because some students need my help to understand simplification process. Just look at board here. 0.931 can be written as 931 divided by 1000. 931 divided by 1000. Multiply by 5 into 60 can be written as 300. 5 into 60 can be written as 300. This minus and positive signs, minus into positive will be minus half 0.001. 0.001 can be written as 1 over 1000. 1 over 1000. These are the methods here. 5 times 60 is 300. 5 times 60 is 300. Square of 300. 5 times 60 is 300. Square of 300 means you should write another 300. That's how you get the square. 5 into 60 is 300. Square of 300 means 300 into 300. Now you can cancel out easily. Look at what here. 1, 2, 3 zeros can be cancelled out with these 1, 2, 3 zeros. Simple. Similarly, here we have 1, 2 zeros. They can be cancelled out with these 2 zeros. So what are the remaining terms here? We just want to multiply. We just want to multiply this 931 by 3. 3 times 1 is 3. 3 times 3 is 9. 3 times 9 is 27. In addition, only 2 zeros cancelled out. In addition, we have number 10 here. Minus. This is 30. 30 divided by 2. What is 30 divided by 2? That is 15. Into 3. 30 divided by 2, 15. Here we have only 3 because all the zeros are cancelled out. Now, 2793. 2793 divided by 10. That is 279. Because of this 10, 1 decimal points will be added. Minus 15 times 3, 45. 15 times 3, 45. So finally you will obtain theta equals 279.3 minus 45. So nothing will happen to the 0.3. 9 minus 5 is 4. 7 minus 4 is 3. 2. There is nothing to subtract from 2. So 2 will be there as it is. Theta, angular displacement, the unit is radian. So theta is 234.3 radian. Who got this answer? Please raise your hand up if you have obtained this answer. Lamai, please raise your hand up in the Zoom chat if you have obtained this answer. Very good. I'm so happy. Nice. Excellent. Good job. Actually, superb job. Very good. Right, so we have reached to the end. We have applied the torque of 7.15 10 to the power minus 3. That torque reduces the velocity of the rotating satellite from 0.931 radian per second, 0.628 radian per second. It takes 5 minutes for that process. During that process, the rotated angle, we found it as 234.3 radian. They ask the amount of energy needed for this process. The amount of energy needed for this process is equal to the amount of work done. So you should know that work done is the change in kinetic energy. We have proved it in our linear motion mode. Work done is equal to the change in kinetic energy. So energy needed for this process is the amount of work done by the torque. So required energy equals work done by the torque. Work done by the torque. Work done by the torque is equal to torque into, we can write tau theta or torque into angular displacement. I'll write this equation completely because there may be some new students. So torque into angular displacement. The torque, we have found the torque as 7.15 into 10 to the power minus 3. That is the torque. Angular displacement, we have found it as 234.3. So amount of energy needed for this process will be some joules, right? Just multiply and tell me the answer. Do it. Send your answer to the Zoom chat. I was waiting for your answers. Is it difficult? That is 1.67. 1.67 joules. Who got this answer? Lamai? Who got this answer? Okay, nice. Excellent. Right. I want to go for a new section. Right. So I think this is a very comfortable way to learn them. You at your home, I am at my home. No disturb from at all. So, and you can ask anything using the Zoom chat. So you should feel that you are in an individual class. You can ask anything from me. Like that, you have a home visited teacher, right? No need to travel. Everything is very comfortable and much easier. I think this is the best way to learn. Only thing is you have to charge your device earlier. And you should have a good data connection. Right. I want to start a new section. So please complete these things and send a message to Zoom chat saying done. Then I'll start the new section, and it is very, very important. It's very important. Right. I think time is enough, so let me erase. Right. Before I start the new section, I want to check whether you remember Newton's laws of motion, because here we need them. For example, right, in Newton's laws of motion, check whether you remember this part. Newton's laws, right? Let's say there is a horizontal surface, and let's say there are two blocks. There are two blocks. Let's say mass of this one 4 kilogram, mass of this one 6 kilogram. Let's say they are connected to each other. They are connected to each other by using a string like this. They are connected to each other by using a string like this, right? And let's say we have applied the force of 20 Newton. So we have worked with so many questions. So because of this 20 Newton force, 6 kg mass is moved to my right hand side. When it is moved, it pulls the string. Then the string pulls the 4 kg object. Finally, everything will be moved with the same acceleration. Everything will be moved with the same acceleration. Normally, in these questions, they will ask you to find the acceleration of the system and tension forces in the string. So because of this 20 Newton force, 6 kg moved, when the 6 kg moved, the string is pulled. Therefore, the string will be in the form of a straight line. If a string is in the form of a straight line due to applied forces, we use it is said that the string is stretched. The string is stretched. So how do you find the acceleration? I want to revise this knowledge. I want to recall your memory. To apply the acceleration to the system, to this direction we apply F equals NV. Once the entire system is considered, the force acting on the entire system is 20 Newton. The total mass of the system is 4 kilogram plus 6 kilogram. The acceleration is 8. That's what we want to find. So 20 equals 4 plus 6 is 10 into 8. So if you cancel out this 0 and this 0, you get 2 equals 8. It means A equals 2 meter per square seconds. Use the same circular and rotational motion book. Use the same circular and rotational motion book, the same book that we discussed up to now. Write Newton's laws and draw this figure and write this calculation. I want to give a brief description about the tension forces, because for the next theory part, I want the tension force. Start there, quick. Right, now look at board here. So we mark the tension forces like this. We mark the tension forces in the string like this. But how these tension forces come here? Let me explain. So if you consider this 4 kg object, it's also moving in the same acceleration of 2 meters per square seconds. For an object to be moved with an acceleration, there must be a force. For this 4 kg object to be moved with the acceleration of 2 meters per square seconds, there must be a force acting on it. Whose law is that here? That is Newton's first law of motion. If you do not apply an object, if you do not apply external unbalanced force on an object, if it is a stationary object, it will be at rest. So the box was initially at rest. It is moved with an acceleration. It means there must be an external unbalanced force. The only thing thing that is able to provide the force is the string. So when the 6 kg is moving, the string is pulled by 6 kg, the string pulls the 4 kg object. The force given by the string to the 4 kg object, I should mark it as capital T. So here I want to find this capital T. So what should I do here? It's better if you draw this figure. You should draw this figure. Only to 4 kg object, only to 4 kg object, to this direction, I can apply F equals mv. The only force acting on the 4 kg object is capital T. Mass is 4, acceleration is 2. Acceleration is 2. So then we will obtain that T equals 4 times 2 is 8. So tension in the string is 8 Newton. If you apply F equals mA to 6 kg object also, you get the same 8 Newton answer. But I just want to find only this T Newton tension force. Draw the figure, right? Only to 4 kg object, apply F equals mA and find the tension in it. Write them here. Start. Right. So why do we want this point there? So when a string is stretched like this, there are tension forces in the string. Now look at board page. Now I'm going to explain a very important section. You cannot answer in the next two sections. It means conical pendulum and vertical circular motion. You need this theory part. So listen to me carefully. Right. Look at board page. Right. Let's say we take a small metal ball. We take a small metal ball and that metal ball is connected to a string. We take a small metal ball, it is connected to a string and the metal ball is moved along a circular path like this. Then what can we observe here? The first observation is the string is stretched. If you take the metal ball, if you connect it to a string, and if it is moved along a circular path, you can observe that the string is stretched. The string is stretched means there must be tension forces as in the previous example. So there should be tension forces in the string like this. So this is a stretched string. This is a stretched string. It's moving with, let's say it's moving along the circular path with an angular velocity of omega. radian per second. It's moving with an angular velocity of omega radian per second. Right? So as the string is stretched, there are tension forces. So if we consider when this particle has reached to here at this position, again you can observe the same tension forces like this. Again, we are able to observe the tension forces like this. If you consider here this position, again you can observe the same tension forces acting on this particle, not the particle, actually the metal ball, right? T Newton and T Newton. If you consider the position when the particle is here, again we have the same tension forces T Newton and T Newton. Finally, look at what. Finally, you can observe one important observation. What is it here? This tension forces directed to the center of the circular path. Here also this tension force directed to the center of the circular path. Even here, the tension force directed to the center of the circular path. I'm talking about the tension force acting on the particle. Acting on the particle. I'm talking about the tension force which is acting on the particle. The tension force which is acting on the particle is always directed to the center of the circular path. It is always directed to the center of the circular path. So finally, we can determine that, we can come to a conclusion that whenever a particle is moving along a circular path, there is a force acting on the particle and that force is directed to the center. Whenever a particle is moving along a circular path, a force is acting on that particle and that force is always directed to the center of the circular path. That force is known as, look at board, centripetal force. That force is known as centripetal force. So our next subheading is centripetal force and centripetal acceleration. Centripetal force and centripetal acceleration. Centripetal force and centripetal acceleration is our new subheading. Under that, please write. Whenever a particle is moving along a circular path, whenever a particle is moving along a circular path, whenever a particle is moving along a circular path, a force is acting on that particle. Whenever a particle is moving along a circular path, a force is acting on that particle and that force is always directed to the center of the circular path. Whenever a particle is moving along a circular path, a force is acting on that particle and that force is always directed to the center of the circular path. Directed to the center of the circular path. Whenever a particle is moving along a circular path, a force is acting on that particle and that force is always directed to the center of the circular path. Full stop. That force is known as centripetal force. That force is known as centripetal force. Centripetal force. Full stop. Leave a line and start a new paragraph. According to Newton's second law of motion, according to Newton's second law of motion. According to Newton's second law of motion, within brackets, look at board, within brackets, Newton's second law of motion means F equal ma. If you take m to this side, you will get A equals F over m. Am I right? If you subject A, it will be F over m. According to Newton's second law of motion, within brackets F equal ma, draw an arrow, A equals F over m, comma. According to Newton's second law of motion, within brackets F equal ma, arrow, subject A, F over m, comma. When there is a force, there must be an acceleration. When there is a force, there must be an acceleration. According to Newton's second law of motion, within brackets these things, comma, when there is a force, there must be an acceleration. There must be an acceleration. Full stop. Therefore, a particle must have an acceleration. Therefore, a particle must have an acceleration due to the centripetal force. Therefore, a particle must have an acceleration due to the centripetal force. Due to the centripetal force. That acceleration is known as, use a different color pin and write. That acceleration is known as, use a different color pin and write, centripetal acceleration. Centripetal acceleration. Right? Star point and write. The following arrangement can be used to identify the centripetal acceleration, centripetal force. The following arrangement can be used to identify centripetal force. The following arrangement can be used to identify centripetal force. Draw this figure. Draw this figure. The following arrangement can be used to identify centripetal force. Draw this figure, quick. Right. I think time is enough for you to draw the figure. I think time is enough for you to draw the figure. So please try. When the particle is moving along the circular path, when the particle is moving along the circular path, when the particle is moving along the circular path, comma, it can be observed that when the particle is moving along the circular path, it can be observed that the string is stretched. When the particle is moving along the circular path, comma, it can be observed that the string is stretched. The string is stretched. Full stop. Full stop. When a string is stretched, when a string is stretched, when a string is stretched, comma, there should be tension forces in it. When a string is stretched, there should be tension forces in it. There should be tension forces in it. When a string is stretched, there should be tension forces in it. Full stop. The two tension forces acting on the string, the two tension forces acting on the string are marked on the above figure. The two tension forces acting on the string are marked on the above figure. Are marked on the above figure. Full stop. Full stop. Leave a line and write one of the tension forces. One of the tension forces is directly acting on the particle, and one of the tension forces is directly acting on the particle, and that tension force, one of the tension forces is directly acting on the particle, and that tension force is always directed. And that tension force is always directed to the center of the circular path. And that tension force is always directed to the center of the circular path. To the center of the circular path. Full stop. Therefore, that tension force is, acting as the centripetal force. Therefore, that tension force is acting as the centripetal force for the particle. Therefore, that tension force is acting as the centripetal force for the particle to be moved along the circular path. For the particle to be moved along the circular path. Therefore, that tension force is acting as the centripetal force for the particle to be moved along the circular path. Right. Now put 3 star points and write. Put 3 star points and write. So unfortunately, this equation cannot be proved in A-level physics. It is out of syllabus. But your applied maths teacher will prove the equation. Right? Look at board. So if there is a particle moving along a circular path, if there's a particle, if it is moving along a circular path, right? If there's a particle moving along a circular path, of radius simple r with an angular velocity of omega radian per second, and if its tangential velocity is v meter per second, centripetal acceleration is given by the equation v omega. This can be proved, but the proof is not in the syllabus because you don't know any maths, right? So put 3 star points and write. The centripetal acceleration can be found by the following equation. The centripetal acceleration can be found by the following equation. The centripetal acceleration can be found by the following equation. Draw the figure, write this equation, and you should wait because I'm going to give you 2 more equations. I'm going to edit this equation and I'm going to give you 2 more equations. Draw the figure, write the equation, and please wait. Start. In this equation, what is V, dear? Come on. What is V? Can somebody unmute the mic and tell me?
Tangential velocity.
Tangential velocity. Very good. What is omega?
Angular velocity.
Angular velocity. So simple, R is the radius of the circular path, right? Just listen to me while you are drawing and writing. Listen to me. Okay. Right. Omega is angular velocity. Angular velocity. V is tangential velocity. V is tangential velocity. AC is centripetal acceleration. A small c. Centripetal acceleration. Centripetal acceleration. Right. Now, what is the relationship between V and omega? Lamai? What is the tangential velocity equation?
V equal R omega.
V equals R omega. Very good. V equals R omega. This is the relationship between V and omega. You should just draw the figure, write the equation, name it, and wait. Now, I am going to use this result. I'm going to use this result in centripetal acceleration equation. What is centripetal acceleration equation here? Az equals V omega. But V is equal to R omega. So in the place of V, I'm going to write R omega. I'm going to write R omega into omega. Then what will I obtain here? What is omega into omega here? Omega into omega.
Omega square.
Omega squared.
Omega square. Very good. So we have taken another equation for the centripetal acceleration. That is AC equals R omega square. Write all of these things. Write them all. We should use the maximum time. We should not waste the time here. We should not waste the time. We should not stop the class earlier. Right. I can write one more relationship. Look at board here. V equals R omega. If I take R to this side by cross multiplication, I can write again V equals R omega. I'll take R to this side by cross multiplication. Then I'll obtain V over R equals omega. I'm going to use this relationship in centripetal acceleration equation, that is AC equals V omega. AC equals V omega. Look at both. This is the most important relationship and this is the most widely used equation. Therefore, listen to me carefully. So, AC equals V omega. V into omega is V over R. Omega is V over R. Now, what is V into V? Lamai? V into V?
Yes, sir.
V squared. So this is the most widely used form of centripetal acceleration equation, that is V square over R. What's the equation that we widely used here? V square over R. Write it here. This is the most widely used form of the centripetal acceleration equation. AC equals V square over R. So you should remember all these three equations. You must remember all the three forms and you must be able to obtain all these three forms. That's it.